Hello, everyone. Welcome back um, to a new week here. So we're continuing our discussion now with Lecture 11 on the discussion of gases, the speed of particles, and the contributions of the real gases to the ideal gas equation. Okay, so we left off calculating the average velocity of an H2 molecule. And you see here, if we know the relative velocity of another particle, we can actually figure out the speed at which something else moves based on the molar masses of the speed. Okay, so now let's talk about another metric here, root mean squared velocity. So root mean square is another way we can measure speed. If we have some gas particles, we can measure. This is kind of like a statistic to kind of describe what speed these gas particles will have at a specific temperature. Okay, so to find the root mean squared velocity of a gas, we can rearrange the kinetic energy equation and find velocity. So let's just write that right here. So we can then use. So usually we have a U sign. Oops. A U sign for speed, root mean squared. So we can rearrange the kinetic energy equation, right? So we know that it should equal speed, and we have 1/2 mv squared. And if we solve for v here, we know that so we can actually rearrange this equation and solve for v. Okay, so we will do, we have two equations we need to consider, kinetic energy and also the kinetic energy of a gas, which is dependent only on the temperature. And we remember that this also equals Ke. And then Ke also equals 3/2 RT. So let's quickly go over why 3/2 RT equals kinetic energy. So for any gas, we can describe the pressure like this. So the pressure of a gas is equal to the amount of particles per given area or volume. In this case, it's the same thing, kind of like space. A gas moves in three directions, right? So we can relate the pressure using the volume from the ideal gas law, and then we can then so that gives us kind of like the density, or like how when a thing moves, it tells us, roughly speaking, what the pressure should be, and then we multiply that by the speed. That will give us the pressure. So we have m. So I'm going to use u here for speed squared. So that describes our pressure. But since there are gases are 3D molecules, they have three directions for which they move. So to take the average pressure, we say, okay, the speed at which a gas moves is going to probably be the same in the x, y, or z direction. So if we draw our coordinate system here, right, the direction a gas moves is going to probably be the same. So we're going to average that out and put 1/3. So it's going to be 1/3. The pressure of a gas is going to be a combination of all three, but the average pressure, since it can move in any of the three directions, we say 1/3 NV mu squared. Okay, so now if we plug this into the PV equals nRT equation, we can solve for pretty much kinetic energy now. Okay, all right. So if we do, if we now rearrange this equation, we will get, let's see here. So let's rearrange our equation to solve before, we're going to substitute P. Sorry, we're going to substitute P here. So 1/3 N times V. Okay. And then this is going to be pressure, right? Times V equals nRT. Okay, so the volumes will cancel out. And now if we times both sides by 3, the fraction will cancel out here. So we get N equals 3 nRT. So to keep things consistent, let's change this N back now to the actual N for molecules, or number of mole particles. So we do moles here, and then the N's will cancel out here, so we get right here. Oh, sorry, I forgot the mu squared. So I forgot the mu squared here. Sorry about that. So let's move this over a little bit. Okay, so now we have mu squared times N equals 3 nRT. Okay. Now, if we cancel, we divide both sides by N. So let's divide both halves by 2. So let's divide both sides by N first. Okay. And we do that, we get rid of the N's here, and we have mu squared over 3 RT. And now if we divide both sides by 2, put a 1 here, divide both sides by 2. Now we get, this equation is our kinetic energy equals 3 halves times RT. Okay. Okay. So that's how we derived that equation I just wrote up there above. So I'm going to erase this now, and we'll talk about how to figure out the average speed, okay? Oopsies. Okay. Okay, so we know that equate these two equations. Okay, so now let's rearrange and solve for velocity. So if we multiply both sides by 2, we cancel out the 2 in the denominator, and we get mv squared equals 3RT. Okay, and then we're going to divide both sides by m, so we get 3RT over m. And then we're going to square both sides here, and we get v equals the square root of 3RT over m. So m in this case is molar mass. Okay? So if we plug this in, this equation in for our previous problem, we'll see we'll get the same answer. So let's do that. Okay. So we do v equals square root 3r times 273 Kelvin divided by molar mass of hydrogen, which is about 2.016 grams per mole. Okay. So these units will have to cancel out somewhere. Ah, right. So, so the units, are a little bit weird. So, but anyway, yeah, so the units in this calculation, they're a little bit tricky. So we'll have to kind of elaborate on that. So R can equal another constant. R has another set of units in terms of when we refer to energy. And we'll talk about this a lot when we talk about quantum mechanics. So it has the units of joules per mole Kelvin. Okay, or joules per mole Kelvin. All right, and we know a joule equals 1 kilogram meter squared per second squared, like that. Okay, so it has some weird units. So joules can also be referred to as a kilogram per meter squared times meter squared per second squared. So that's just units we'll have to know, and you'll be given this, but you don't. To kind of delve in why that is, we'll have to take a look into physics. But I don't exactly recall why the units are like this. I think it's just the definition for joule. So like for each unit, you need a kind of a reference point. So this is also like kind of where we go back to standard units, where we can describe the energy or unit of joule as per 1 kilogram per meter squared. Times meter squared per second squared. Okay? So in this case, we will have to convert this to kilograms per mole. So that'll be 2.016 times 10 to the negative third kilograms per mole. Okay, so in this case, the units will now cancel, right? Because kilojoules will cancel. And then your moles will cancel and your kelvins will cancel. So all you have left is meters per second, because you would square root it and it will turn into meters per second. Okay, so if we do this now, okay, so the constant here is a little bit different. It's actually 8.3145. So they have, if there's different units, it's going to have a different value, right? So that's why we use this value instead of the 0.08206. Okay. And now if we kind of do this calculation here, we get 3 times 8.3 times 273 divided by okay, and if we do that, we get our answer turns out to be 16.89 times 10 to the third, no, not times 10 to the third, sorry, meters per second. So it's pretty close. So you see here that they do give you the same speed. Now they're not quite really accurate because it's just because of a method of doing it. One uses constants and one doesn't, and it depends on how well we use the molar mass. So if I probably use a more accurate molar mass in the previous example above, we'll probably get the same answer. Okay, so you can also use that equation as well. So you need to find the speed of anything, like the speed of any particle. You can also use the root mean square speed. That also tells you kind of a metric of the average speed. But instead of just taking the original average, it just you don't have to do that kind of. You don't need to know all the speeds. but it tells us that the speed is only dependent on the kinetic energy and the mass. So we don't need to take into account like the speed of all the other particles. We can just consider the mass of the particles in general. Okay, so that is root mean squared speed. So these equations will be provided for you, so no need to memorize them, but just know how to use them and make sense of them on exam, so you know when to use the equation, so you don't get in a stump during an exam. Okay, so let's look at here. This is what we call a Boltzmann distribution. So just like I showed you for kinetic energy, as the temperature increases, you're going to get molecules with a greater distribution of speed. So at the higher temperature, molecules are going to have more energy. So there's more energy to disperse between the molecules, and that's why at higher temperatures, the curve broadens and becomes wider. And the most probable speed, which is kind of the speed at which most molecules move at, is going to increase because you have more energy for your gas particles to move. Okay. All right. Okay. So we see here, the lighter the gas, the faster it moves. Makes sense because these particles, they have different masses, more masses, or molecular weight. So the smallest particle should move way faster. Okay, and kind of you could kind of think of it like certain smells don't escape the room as quickly, and that's because it has to do with the speed of the particles at a given temperature. Okay. All right. So let's talk about how gases kind of behave in a closed space, or like how gases behave like within a partition or like a divider. Okay, so now let's talk about Graham's law of diffusion and effusion. So diffusion is the rate at which two gases mix or mix together. So on, I think last week's participation questions, I had a simulation as one of the problems, and you get to solve how gases diffuse through a divider. So if you haven't looked at that, I will take a look, because it'll kind of, I think it'll be better help visualize what these things mean, or how diffusion works. Okay, so what happens is we can measure the rate of diffusion can be studied with this apparatus. So we use this like porous membrane at the top there that to help kind of illustrate diffusion between the air and the gas within the tube. Okay, so the gas escapes from the tube faster. We can estimate like what's happening first. Is the hydrogen gas escaping into the air faster, or is the air diffusing into the tube of water? And if you can take a look, if the rate at which the gases enter or leave, if air enters the tube, the amount of water in the tube will increase, right? Because it'll push the water down, and it'll just overpower the opposing pressure from the hydrogen and push the water up through the tube. Okay. Yeah. Okay. Oh, sorry. No, I didn't got that backwards. So yeah, there's actually two tubes. So if hydrogen is moving faster, right? It's going to push water into the tube. So the gas pressure will push the air into the tube. It'll push the water up the tube if gas escapes faster, because when you do that, you're displacing volume, right? So the water level will rise. Okay. And now, if the opposite is true, if water is entering faster, then water will be displaced from the tube because it'll be pushing the water out and back into the larger reservoir there. So we can tell, we can determine the rate of diffusion here by comparing it to air. And usually, if the lighter the molecule, the faster it will move. So probably the faster it will diffuse. And then the heavier the molecule, the slower it moves, and it'll diffuse more slowly. Okay, so that's diffusion. So diffusion and effusion can be confusing. They seem like similar terms. And in the next video, we'll go over effusion next. Okay, so I'll see everyone then.